Hello ET Capstone stakeholders, my name is Joseph Nopum, Grantham ID G00147188, and today I'm going to show you the automatic plant watering system. As I have no team, this project was researched and designed solely by me. What I'm going to show you today makes use of many of the concepts I learned while at Grantham University. My project takes on the issue of plant watering that routinely gets forgotten by most people. I made it my goal to design an inexpensive automatic watering system that would alleviate the issue for a certain number of days. The end user and target audience is anyone who would like to ensure their plants are watered in their absence or due to forgetfulness. My original design was rejected due to lack of complexity, and it was recommended to use wireless connectivity. So this design is different from any other on the market right now, as it includes wireless connectivity. I did a lot of research into using wireless connectivity, and through cost analysis, I determined that the commercially available, off-the-shelf 434 megahertz receivers and transmitters were ideal for this project. Much of my research involved a very helpful book titled Arduino Remote Sensing and Control using 434 megahertz modules. A lot of other research was done utilizing the data specification sheets and other helpful links on the Spark Fund and Marlon P. Jones and Associates websites. The key objectives for this project were, of course, a functional project, getting the two Arduinos to talk to one another, and finding a way to power this pump outside of the Arduino's power supply due to the limits on the Arduino's power supply of 500 milliamps. The key constraints that I had for this project were to keep the voltage under 48 volts to prevent shock and prevent any sharp edges to prevent cuts. The basic functions of this project include a measurement of the soil moisture, a call for water, and a delivery of water until the water is out or there is no longer a call for water. Some other designs I researched included the use of a large rainwater collection vessel that would be tied to a downspout diverter on my house. This would have alleviated the need to periodically refresh the water supply in my smaller vessel. Another design included cutting a T-fitting into my water service line and delivering the water through the opening and closing of a solenoid valve. The key metrics that bore heavily on my choice of design were the cost and level of difficulty the consumer would encounter. Both of the aforementioned designs were deemed too costly and would not be something a normal customer could install. That's why this prototype was chosen for its low cost to design and its relative ease of installation. All a consumer would have to do is fill up the container when the red LED came on, which signified a low water condition, and place the wired probe into the soil. The key features of this design that stand out are its wireless connectivity and the fact that it's solar powered, as you can see by this panel right here. If needed, this model could be scaled up to deliver water to farms in areas that are not currently on a power grid. My proof of concept testing was done through the individual testing of each and every component, and then subsystems, and then the transmitter and receiver portions, and then all together as a completed prototype. Now I'm going to show you how the project works. The project works on this soil moisture sensor is looking for a moisture of 45%. If that moisture is less than 45%, a call for water will be made from the transmitting Arduino to the receiving Arduino. In turn, the receiving Arduino will look for that digital 1 from the transmitter and a digital 0, which means there is water in the tank. Those two conditions make up the AND statement in my programming, and if those two conditions are met, the digital relay will close the contacts and it will be fed power from my solar charge controller, and that will pump water from my tank into the soil. When this calls for water, a blue LED light will come on. When the relay is engaged, a red LED will come on the relay, And if a red LED comes on over here, that means the water level is low. I will now demonstrate the project. I'm going to turn on the battery. These are AA, 8 AA batteries that feed my Arduino 12 volts. Okay, everything is on. The solar charge controller now has 14.4 volts of energy, and it's also got the battery backup. Now, since my soil is at or above the 45% moisture threshold, the pump will not activate. So I will manually pull out this moisture sensor to trick it into coming on. The call for water has been made, and it pumped water into my soil. Once I place the probe back into the soil, it stopped pumping. I will now show you that the call for water, the low level control works when the vessel runs out of water. I will let it pump until the water is empty. As you can see, I hit a low water condition and it stopped pumping. To wrap things up, there are some improvements that need to be looked into in this project. The pump flows water rather quickly, as you can see, and if it puddles up when the call for water ends, the soil will be siphoned back into the vessel. A check valve installed in series between the pump and the discharge end would alleviate this concern. Also, I initially wanted to include a mister on the discharge tubing, but I was worried that the circuitry on my sensor would be damaged by the water, so I did not do that. Hindsight, I probably should do that and just put some silicone or other sealant on the content or the circuitry on the moisture sensor. I would also like to do something about these battery packs, as these both hold 8 AA batteries apiece to give 12 volts to my Arduinos. If I could find a way to drop those from the design, that would be good. That would definitely be a value-added benefit. All right. Although this project is small, I hope that this demonstration today has sparked your curiosity into what can be done with wireless connectivity on a much larger scale if needed. Thanks for watching.